Hi everybody, today we're going to talk about the last topic related to particle motion, and that is displacement versus total distance traveled. You're going to need to be able to find both given any position function s of t and distinguish between the two. So let's take a function here, and we're going to start with an exponential function. And I'm going to say that this exponential function describes my particle's path, and let's go for the first 8 seconds of movement here. So take a second and write down what we're looking at. Before we talk about anything else, I just want to look at the graph with you all so you can see characteristics of the graph and how that can help us find displacement and total distance traveled. So on my TI calculator, I'm going to graph my position function. I'm going to go ahead and check out what's going on here. All right, so clearly it looks exponential. Now keep in mind this is the position graph. So it's not that the particle is actually going up in the air. It's just that on the x-axis for each time, the y values tell you its position on the x-axis if we were to look at it left to right. Now notice that our position function is increasing. And if a function is increasing, that means its derivative is always going to be positive. Picture tangent line slopes, they all have a positive slope. So if position is increasing, then that means the velocity is always positive. So position is increasing. That's the same as saying f is increasing. That means the derivative, which is velocity, is positive. And if velocity is positive, we know our particle is moving right the entire time. So I'm going to graph this parametrically for you, and then we're going to see again that it is going to move right the whole time. So I went on my calculator, I went to parametric mode. I want to see the actual movement on the x-axis so I can clearly see what the path is. I'm going to hit graph, and here's my particle. It starts moving right slowly and then quicker and quicker and quicker. So it's clearly increasing in speed. The thing I really want you to focus on is the fact that this particle is always moving to the right. It's never changing direction. And again, that was because the velocity was always positive. So let's go back here and let's go ahead and find the displacement of this particle. Our goal is to find the displacement for, let's go from t equals 2 to t equals 6. Let's find the displacement. And in the first particle motion video, I told you displacement is the net change in the position from the ending position to the beginning of the position, regardless of what happens in the middle. It doesn't matter if it repeats and goes back on itself many times. You just care about the net change in position. So to find the displacement, let's find where the particle is at 6 seconds. And let's find where it was at 2 seconds. So at 6 seconds, it's t to the 6 over 2. So 2 cubed, which is 8. And then at 2 seconds, it was 2 to the 2 over 2, which is 2 to the first, which is just 2. So at 2 seconds, it started at 2 on the x-axis. At 6 seconds, it was at 8. So clearly, the displacement is a total of 6. I got that by doing s of 6 minus s of 2, 8 minus 2. Now, this might seem very basic, but it's important that you realize how we find this, because once we get to the more difficult ones, this basic concept is going to be used over and over again. And sometimes people forget this basic concept whenever things get tricky. So it is displaced 6 units. You subtract the ending position and the initial position. So what I want you to do is make sure you have that worked down. And right here, to find the displacement of any particle between time 1 and time 2, you take the position at the ending and subtract the position at the beginning. You just subtract the endpoint positions. Now, this displacement is 6, and our question is, what is the total distance traveled? Because there's technically a very big difference between the two. In this case, since the particle is always moving to the right, the displacement is 6, and the distance it traveled from t equals 2 to t equals 6, that should be a 6 right there. Whoops. From t equals 2 to t equals 6 is the same as the displacement. and I want you to make a note that the reason that total distance traveled and displacement are the same is because velocity didn't change sign. Didn't change sign. Another way of saying that in terms of position is the particle didn't change direction. Because in order for a particle to change direction, velocity would have to change sign. So take a moment and think about that. The particle always moves right. So from 2 seconds to 6 seconds, it's always the displacement and total distance traveled will be the same. Now we're going to look at a slightly more complicated example than this one here. Side note, I should not have changed that 8 to a 6. I just messed myself up here. This is the position is 2. This is the position is 8. I'm at 2 at 2 seconds. I'm at 8 at 6 seconds. You subtract them to get 6. Sorry about that. So let's go to one that's slightly more involved here. So we have all the notes down on this sheet here. Make sure you wrote down this little formula because you're going to need this formula a lot in class next time I see you. And let's go to this function. It's a quadratic. And I'm going to call this function the position again. I'm interested in the first 8 seconds, or I'm considering this function for the first 8 seconds. I want to find the displacement from 2 seconds to 4 seconds. So let's use our formula. Displacement's the easy one. You just take the endpoints and subtract them. Let's find S of 4. That'd be 4 squared minus 6 times 4. So 16 minus 24, negative 8. And let's find the position at 2. When it started, 2 squared minus 6 times 2, 4 minus 12, negative 8. Uh-oh, if I subtract these, S of 4 is negative 8 minus S of 2 is negative 8, 0. Now, that doesn't mean that the particle didn't move at all. It just means the displacement, the change from the beginning to the end, is 0. Because at 2 seconds on my x-axis, I'm at negative 8. That's my position. That's an S for S of t. My position is at negative 8. And at 4 seconds, I'm at negative 8 again. So this particle did stuff between 2 and 4, but it ended up where it started. So let's take a look at the graph here. And let's see what happened in between 2 and 4 seconds. So I'm going to go on my calculator. So I'm going to first graph normal function mode because we want to be able to analyze the position graph. So again, this is the position. My position starts off decreasing and then my position increases. So here's 2 seconds, here's 4 seconds. You can see that the position at 2 is the same exact height or position at 4. Now, if a function, the position or f, is decreasing, that means the derivative, which is velocity, is negative. If the function is increasing, then the derivative, which is velocity, is positive. If velocity is negative, that means the particle is going left. If the velocity is positive, the particle is going right. So let's look at parametric mode just to let that sink in one more time. Here I have a graph of the position, and I'm making y be 0 because I only wanted to move on the x-axis. I'm going to graph this. So it starts at time 0 and moves to the left. Then it backtracks, and then for the rest of its movement, it's going to the right, going faster and faster. I'm mainly concerned with the fact that at some point it's going left, then right around here it changed direction and went right. So velocity was negative, and then at this point velocity was positive. So let's go back to our notes here. Come on. There we go. We've already established that the displacement is 0. What we care about now is finding the total distance traveled. Make sure you note that the particle changed direction because the velocity changed sign. And what we realized is that at time equals 2, our particle was at negative 8 on the x-axis. It was moving left. And then it changed direction and moved to the right such that at time equals 4, it was back at negative 8. So whatever distance it moved to the left and whatever distance it moved to the right, they're the same exact thing, which is why when we found displacement, it was 0 because this negative and this positive canceled. I want to add the magnitude of these two individual distances. I don't want this blue one to be negative and cancel out the yellow one. So I really need the absolute value of the distance when the particle moved left and the distance when the particle moved to the right. So again, we need absolute value here. And here's the key of what we're going to be doing. I want you to write this down and make sure you really understand why we have to do this. If velocity changes sign, meaning that the particle changes direction, during the time interval you're interested in, to find total distance traveled, you need to split up the time intervals into the times when the velocity is positive and when the velocity is negative, and then add the absolute value of each distance. And again, this is to find total distance traveled, which is more work than finding displacement, because displacement, you just subtract the endpoints. Total distance traveled is another story because you need to split it up because I don't want these distances to cancel each other out. So let's go ahead and split up our time interval into times when the particle is moving left and when the particle is moving right. So I need to find out when the particle changed direction, which is whenever time is 0. So particle could change direction. Changes direction. I should say potentially because we're going to check to make sure. So let's take our position. That's s of t, which is t squared minus 6t. Let's take our velocity and let's set it equal to 0. So velocity is equal to 2t minus 6. I'm going to set it equal to 0. I want to solve for t. I get 3. 3 seconds is when the velocity is 0. You need to make sure that the particle is actually changing direction. Don't just assume that because the velocity is 0, it changes direction. Even though we already know it does change direction because we looked at the graph, that's not going to be the case for pretty much every problem you do in this class. Because what could happen is a particle could be moving to the right, stop, and then keep moving to the right. So velocity was 0 there, but the particle didn't actually change direction. So you need to test to make sure the velocity changes sign. And that is the first derivative test. So this is the first derivative test. And make a note to yourself, this is to make sure velocity is changing sign. So let's do a test point. I'm going to do like 1 and 4. Velocity at 1, 2 times 1 minus 6 is negative. Velocity at 4, 2 times 4 minus 6 is positive. Yep, velocity is changing sign, so the particle is changing direction at 3. So what you need to do is find the movement from 2 seconds to 3 seconds, which is blue, and then find the movement from 3 seconds to 4 seconds, which is yellow. Take the absolute value of those distances so that they don't cancel each other and just add those two up. Now that I established that it's changing direction at 3 seconds, what I'm going to do is split it up from 2 to 3 seconds and from 3 to 4 seconds, because I really want from 2 to 4, but you have to break it up wherever it changes direction. And you just find the little displacements in between. So I found the displacement from 2 to 3, then the displacement from 3 to 4. I'm doing the absolute value of each because I don't want this negative to cancel with the positive 1 anymore. So I'm dealing with 1 and 1. So again, what that means, looking up here again, is that it moves 1 unit left and then 1 unit right. So then once you get your individual little baby displacements and you do the absolute value of them all you have to do is add them up, and that gives you the total distance traveled. And in this case, it's very easy just to do 1 plus 1 and you get 2. They're going to get a little more complicated, but again, you must find when velocity is 0, check that the velocity is changing direction, and then split up your interval wherever the velocity changes direction. Find the little baby displacements, absolute values, add up those little baby distances to get the total distance. All right, I'll see you in class and we'll practice long block. Bye.